Ragazzi, io volevo fare un sondaggio rapidissimo. Io questo seminario lo faccio in inglese. Voi preferite inglese o italiano?
No, vedo la sala, perfetto, sì. Un'informazione, ci sono esterni alla scuola?
Vuoi italiano?
Ci sono esterni alla scuola, giusto per curiosità?
Sì, sono esterni, sì.
Facciamo misto allora. 70%.
Quanti?
No, come preferisci, insomma. Tutti parliamo in breve.
Voi cosa? Sì, un'altra lingua avete scelto?
Ok, vi chiedo solo un favore, siccome abbiamo lo streaming registriamo tutto, di usare sempre il microfono, perché sennò chi è collegato non sente niente e poi si perde quello che dice.
Aspetta, è questo qui il microfono?
Credo che funzionano tutti, sì. Lucia chiede qualcosa, ma non capisco.
Ok.
Perfetto, grazie.
Sì.
Allora, io direi di cominciare e fatemi presentare un attimo Domenico, che ringrazio per aver accettato il nostro invito. Io sento un ritorno pazzesco.
Io credo
Comunque,
che sì.
ringrazio Domenico per aver accettato il nostro invito. Conosco Domenico fin dagli albori degli studi, perché lui è stato il mio supervisor della tesi di primo livello, tesi di laurea di primo livello. Ho conosciuto Domenico come una persona estremamente in gamba, estremamente gentile, e poi negli anni si è spostato in California al Caltech per un postdoc, è stato lì 4 anni, credo, forse qualcosa più di
Sì,
4
4 anni e
anni.
mezzo. 4 anni e mezzo.
Esatto, 4 anni e mezzo con proprio la supervisione di Eric Water, che è un professore di fisica e material science a Caltech. E poi subito dopo ha avuto una posizione da assistant professor a Brown University, che per chi non lo sapesse è una città in un piccolo stato, credo uno dei più piccoli degli Stati Uniti,
Il più
Rhode
piccolo.
Island. Ah, il più piccolo, ok, però l'università è assolutamente una delle migliori università, quindi credo sia contento dell'università in cui si trova.
Sì,
E
sono
lì come
stato.
assistant professor per questo semestre è a Catania perché è in sabbatico, quindi sta passando il semestre a Catania e grazie a questa cosa l'abbiamo intercettato e invitato a scuola. Lui appunto all'inizio si è occupato di scienze dei materiali, di nanostrutture di silicio, interazione con ergio, poi è passato a studiare plasmonica e adesso continua a studiare plasmonica, in particolare interferometri plasmonici utilizzati come sensori. Credo che adesso lui vi spiegherà un po' meglio cosa fa esattamente. Tra le tante caratteristiche di Domenico c'è quella di essere estremamente chiaro quando spiega, quindi approfittate di questo suo seminario e fategli tutte le domande che ritenete opportuno, perché credo sia un'occasione importante per voi per capire un po' questo campo della fisica e la plasmonica, che è un campo abbastanza nuovo, ma che ha dato risultati molto interessanti negli ultimi 5 anni. Adesso siamo un po' organizzati così, passo la parola a Domenico che farà il suo seminario, alla fine ci saranno le vostre domande. Siccome io purtroppo ho un impegno, vi devo salutare adesso e chiedo poi ad Antonio Dio di moderare la parte delle domande e poi appunto avrete modo di parlare con lui anche dopo, fin quando non vuole andare a casa sui bambini, non lo chiamano. Va bene, grazie, buona serata e benvenuti a coloro che non sono allievi della scuola, benvenuti a scuola.
Okay, thank you, Emanuele.
Grazie.
Thank you for inviting me here. It's a pleasure to be here, and I'll try to give my best. Actually, I'll try to live up to the expectations because now he has raised the bar. As I said, oh, this is too loud. Okay, so this is my group, Brown University. You can see graduate students here. This is a visiting student, Salvo Cosentino. Some of you know him. Thanks to Tony, he came by and spent some time at the university, at Brown University. But mostly, I consider this my graduate students. This has graduated, now is working at NIST. Patrick, Pei, and Jing are still in my group. Vinci is now a senior scientist at BD, which is a biomedical technology enterprise. And these are undergraduate students. In particular, Khan, Abby is still working with me. Emily is at Berkeley, Alec is at University of Virginia, Natalie is at the IBM, Drew is at Max Born Institute right now. I'll try to tell you a little bit about the research that we do at Brown University, in particular focusing on plasmonic interferometry, the physics and applications of plasmonic interferometry. I was told I have about 45 minutes, but if you feel like there is something you would like to understand better, stop me anytime, ask questions in Italian and English as you like, and I'll answer accordingly. So first of all, if we want to understand plasmonic interferometry, we need to understand plasmonics and interferometry independently. So first we're going to talk about surface plasmons. In particular, we're going to talk about the physics of generation of surface plasmon polaridons. And I'll show you how individual scatterers that are made on metal films can be used to excite surface plasmon polaridons that are basically nothing but electromagnetic waves that are coupled to free electrons in the metal. I'll also talk about applications, in particular photovoltaics, so plasmonic solar cells, high throughput plasmonic biosensor, plasmonic ellipsometry, optical coherence meters. Again, there is a lot more material than I can cover in 45 minutes, and perhaps I'll skip a few parts. But since we have time until 10:30, and then there's going to be a question and answer session, maybe we can integrate the question and answer session together with my talk. So stop me at any time. So first of all, what is a plasmon? So from plasma oscillation, a plasmon is a density fluctuation in a fluid of free electrons. So if you take a metal, you have a lot of free electrons, the density is pretty high, and the frequency of this plasmon is in the range of hundreds of terahertz, so in the visible range. Surprisingly enough, the sun also is able to emit plasmons, but they are in the order of tens of hertz or kilohertz. So we cannot see them, but we can measure them as well. So if you take a small particle, you can have localized surface plasmons. So the idea is that you come in with this electric field. The electric field can couple with the electrons in the metal, and the electrons will start to oscillate back and forth following the field. At a specific frequency and also the specific color, there's going to be a resonance, which is called the Plasmon Resonance, and that resonance actually determines the presence of strong absorption in the particles. What happens at the resonance is that you have an out-of-phase mode, and this phase is pi/2, offset with respect to the incident field, and you can see an accumulation of charge at the surface. So this is an effective motion of the entire electron sea. Okay, so all the electrons are moving in the same direction, and they are oscillating, and they are displacing. Actually, there is an electric displacement that we can measure and quantify. We also have a different kind of plasmons. They're still generated using light, but this can propagate along the metal-electric interface. In particular, if you come in with a certain beam, you can generate you can generate oscillations of the electrons along the plane, and this oscillation can propagate away from the source origination of these plasmons. Of course, the plasmon modes rely on the fact that since electrons are charged particles, you can couple charged particles with electromagnetic fields, and therefore you can excite surface plasmon using photons, for example, visible light, the laser I'm using here. Now, the ancient Romans knew about plasmons. Actually, they knew how to use plasmon. You've seen this perhaps several times, especially if you've studied plasmonics in the past. You can see this is a typical cup. It's called the Lycurgus cup. It's a Roman cup. And if you place a white light source inside the goblet, you will see red light in transmission. And if you shine light from the side, you're going to see green. So this is a very peculiar property of this glass. It's called a dichroic glass. And the reason it behaves like that is because of small, tiny particles that are metallic in nature and determine the resonance conditions, as I'll show you here. So as you can see, if you have this small particle and you are exciting it with an electric field at a specific frequency, let's call it omega naught here, you have a pi/2 phase, so 90 degrees phase shift between the incident beam and the surface plasmon. And there is a big amplitude, means that basically you have a concentration effect. So all of the field lines are concentrating at the location of the particle. And when that happens, also you have a specific effect occurring in the polarizability of the particle. If you see, the polarizability is determined by the dielectric constant. Epsilon is the dielectric constant of the metal. In other words, epsilon is related to refractive index. Okay, so any material has a refractive index. Epsilon is a function of frequency, which means it's a function of color. And you can see that there is a denominator here. Now you have epsilon plus 2 epsilon d. This is the dielectric constant of the metal, and epsilon d is the dielectric constant of the particle. Now, do you guys know what the dielectric constant is for a metal? Is it positive or negative? Some of you have taken physics 2, fisica 2? Qualcuno di voi? Ok, alcuni di voi. The dielectric constants of metals are negative and big in amplitude, okay, big in magnitude. So for example, for silver, you can have values of the order of -10, -30. Now, you can go from, of course, from positive values to negative values. And you can imagine that if you were using glass, epsilon d for glass is of the order of 2.2. Okay, so you take 2.2 times 2 is 4.4. And now you can think about a specific frequency at which the metal, the electric constant, is equal and opposite to the electric constant of the dielectric material. So what happens when that condition is met? So this goes to 0, and it diverges. Ok, divergenza. So va all'infinito. In pratica, la polarizzabilità va all'infinito. So the polarization goes to infinity, and you can see this field localization at the particle itself. When that happens, for example, if you take gold in glass, like in the Lycurgus cap, that happens at a specific frequency. So this is the absorption coefficient or cross-section. And you can see that there is a peak at 520 nanometers. 520 nanometers is close to the color you see from my laser pointer. It's the green. You can also see a lot of scattering occurring at the same wavelength, a little bit shifted, but basically roughly the same. So 520 nanometers. So what does it mean? If you come in with white light, and white light is made of many colors at once, the green light is absorbed much more than red. Therefore, in transmission, you will see red. And the green light is also scattered the most. Okay? So now you can see how this works. Because of plasmonic effects, you can see how you have high transmission in the red, and you have high reflectance in the green. The origin of the process is exactly the same. It's the surface Plasmon resonance at the metal particle. Okay? Of course, the Romans didn't know it exactly, but they kind of came up with a recipe that worked, and they were kind of lucky in this. This is a little historical perspective of what happened after this Lycurgus cap. Maxwell equations, some of you have studied them. In 1899, Rayleigh tried to explain the color of the sky. And that's again due to scattering by tiny particles. Drew the model for metals. This is the Me theory that described the general optical properties of small particles, rigorously, analytically correct. And then in the 70s, actually 60s, 70s, Ricci and Otto and Kretschmann came up with a way to excite surface plasmons that are not localized, but they can propagate along the metal dielectric interface. This has been a revolution because this device is now used as a benchtop device in biomedical applications. You can buy the BioCore system, which is using surface Plasmon resonance to measure, for example, binding events in proteins. So we'll talk about this a little bit more in details. So if you take a look at what's been done with plasmons. So take a look at the, current days, nowadays, in 2000, 2010. Now particles are used for cancer therapy. It's pretty simple to understand why. If you think about the particle and the Plasmon resonance, there is a lot of absorption and there is a lot of scattering. So now if you tune the particle to absorb in the infrared, say 800 nanometers, 800 nanometers can penetrate, it's red. So the green cannot penetrate. As you can see, there is no light transmitted. But if I had a red laser, you could see some red light coming through. So infrared photons like 800 nanometers can penetrate deep into human tissues. And if you have a particle that has been engineered to show a Plasmon resonance in the red, that can absorb that light. It can increase its temperature and also the temperature of the local environment. And therefore, if you have a cancerous cell or tumoral cell, you can kill it because you only need a few degrees of temperature increase to kill it. So this is what Naomi Hallas is doing at Rice University. And now the model, actually, the technique has been studied by FDA for approval. There's also other things you can do. For example, this is Stefan Meyer's work. You can place small particles one next to the other, and you can excite one. Okay, so think about sending electromagnetic wave. You generate a plasma, and this oscillation will propagate by basically tunneling through the different particles. So you're going to have a carrier of information from this point to that point, and you can see a dye light up at some point. You can also use plasma particles to sample the neural activity of the brain, and you can also measure, use plasmonic particles for biosensing. The reason is very simple. If you remember the polarizability, remember there was a 0 in the denominator. That 0 occurs at a specific frequency depending on the dielectric constant for the materials. Now, if you change the dielectric environment a tiny bit, you'll have to track the frequency. You'll have to change the color to see the resonance. And you can turn this into a powerful detector because now the plasmonic resonance condition will tell you whether there's been a change in the refractive index of the dielectric material surrounding the particle. And for example, you can measure binding events. There is also some studies that have been performed to show that you can use actually propagating surface plasmon for many applications. For example, if you're familiar with silicon-based photoelectronics or optoelectronics, you can think about optical waveguides that can carry optical information. Think about the fibers that can carry information for internet. You can have silicon waveguides that are typically of the order of 200 nanometers in cross-section. That's very big compared to the typical CMOS devices where the gate can be as small as a few nanometers. So in order for you to scale down a computer and make an optical computer, what you need is something that bridges the gap between fiber, optics, and devices. And this is actually provided by plasmonic modulators that actually can be much smaller in size than the typical dielectric materials. This is the BioCore system that I was mentioning before that uses the Kretschmann configuration. So the idea is you come in with a polarized light. There is a prism. We'll see why we need a prism. And you can see reflected light. There is some dark bands that are due to the excitation of surface plasmons. Every time you excite a plasmon, you get some kind of absorption, and there is no light transmitted that actually reflected back at that angle. And therefore, you can sample the binding events occurring at the metal surface. In this case, it's a gold surface. So if you have your linkers, you come in with your antibody. This is your antibody. You can come in with your analyte that you want to recognize. And once there is a binding event, the plasmon will change resonance, and you can see a difference in the dark band here. Also, plasmons have been shown to behave like waves, and waves can interfere. We'll talk about interference later on today. In particular, I wanted to tell you a little bit about how many of you have heard the word interferometry, optical interferometry? Some of you? Okay. Well, you've seen ripples in the pond, right? You've seen if you throw a stone in a pond, you can see oscillations in the water surface, on the water surface. And if you have two such oscillations that can interfere, they build up, and you get a wave that it's twice as tall as in the original wave. But even before this simple example, Newton in 1717 discovered the Newton's rings. You can see those when you place a plano-convex lens like this one on top of a glass substrate, on top of any slab of glass. And you can kind of see them here. Okay, so this is at a specific wavelength. You can see dark and bright bands. And that's the result of interference. The idea is that light is characterized by amplitude, it's characterized by color, but there is also an important quantity, which is the phase. And if you have two light beams that are in phase with each other, they, of course, interfere. They sum up their amplitudes, and you get an amplitude that has twice as much as the original amplitude. What about intensity? We had to talk about this later on, but what about intensity? Intensity of light is? The square of the amplitude, right. So you get how much intensity enhancement? 4. Okay. So you can get up to 4 in this central region, and then you get 0. You can also get 0. So you can have two beams that propagate, and they cancel out each other perfectly so that you get 0 light. You get a dark band in this ring. There's another experiment. Some of you, well, most of you in physics. How many of you are in physics? Okay, so you tell me about this experiment. What is this about? The speed of light. In particular, showing that the ether doesn't exist. Okay, and then this gave Einstein an opportunity to actually generate his theory. Okay, this was a puzzle back then. They were expecting to see a difference if you rotate the table, but indeed there was no such a difference, and that actually caused Einstein to generate his theory. Now, generally, an optical interferometer is made of a light source, coherent. We'll talk about this toward the end of the talk if we have time. And then you have a beam splitter. It's a half silver mirror. Typically, you want to use a 50-50 beam splitter because you want to make sure the amplitudes are roughly the same, comparable. So you have half amplitude here and half amplitude there. You go back, there is a mirror here. And at the detector, what happens is that usually you get constructive interference if the phase difference between the two beams is an integer number of 2 pi, right? So you can get constructive interference. But you can also get destructive interference. You can get 0 intensity or very small intensity if you choose the length such that the optical path is half a wavelength apart. Okay? A modern-day application of interferometry is LIGO, Caltech. It's the Laser Interferometer Gravitational-Wave Observatory. Have you heard about this? So they're trying to detect gravitational waves. And if you think about gravitational wave, the same thing, we talked about the pond, the wave in the pond. We can talk about light. We cannot see the wave nature with our eyes. But if we think about gravitational wave, we are talking about wavelength that are kilometers. And therefore, you need an interferometer arm, which is kilometers in length. Okay? So you have 2 arms at right angles. You have a laser beam that's huge. You have a lot of optics to try to compensate for distortion and aberration and things like that. You have speckle patterns, all sorts of things. But now they are so good they can measure 10 to the minus 15 meters. That's what they claim, okay, 1 femtometer. So what happens if you have a gravitational wave coming in? When one arm will be stretched in one direction, the other arm perhaps not. And therefore, you're going to cause a change in the phase of the laser that's been going in the 2 arms. And therefore, by looking at interferometry, if you see constructed interference, you get in-phase information. Distracted interference out of phase, you can measure a gravitational wave. Okay, that's the idea. What we're trying to do in my lab is to take all of this and scale it down to the scale of micrometers. So we're talking about not kilometers, 10 to the 6, actually 10 to the 3rd meters, but we're talking about 10 to the minus 6 meters. So we have 9 orders of magnitude smaller devices than what used here. And generally, this one is a tabletop device with length of the order of meters. So we're going to talk about micrometers. First of all, I have to tell you that there is a problem when you want to excite a surface plasmon polariton. The problem is that if you look at the dispersion relation of light in glass, you roughly get a straight line. This is called the dispersion relation of light. Omega versus k, or energy of the photon versus momentum of the photon. You have a straight line in vacuum. Omega is equal to ck, okay? And the slope is the speed of light in vacuum. If you have a glass material and you propagate light in the glass, there is a dispersion. So the straight line is no longer a straight line because there is dispersion at different frequencies. So it's a little bit bending, okay? You see it here. Now, what about the surface plasmon? Well, the surface plasmon has an energy dispersion diagram like this, the solid line, which is very interesting. It's intriguing. You can see that it bends away from the light line, and then it curves back, and then there is another branch here. Okay, this is called the radiative surface plasmon. This is called the bound, and this is actually the standard surface plasmon polariton. What happens is that if you choose a photon, say UV or violet, the typical energy for a photon in the violet is 3 electron volts. And you can see that at 3 electron volts, you have a momentum for the wavelength in glass. But there is a different momentum for the surface plasmon at the glass silver material interface. You all know from physics that in order to excite something or to, in a collision, if you have a collision, you have to conserve energy. and momentum. Okay, so what's the problem here? The energy is already conserved because the electrons oscillate at the same frequency. But what about momentum? Momentum is not conserved. There is a mismatch. There is a difference in momentum. So delta K is a mismatch. Therefore, you cannot excite the plasmons by simply shining your laser onto the mirror. So if you shine your laser onto the mirror, there is no surface plasmon generation. The reason is energy is conserved, momentum is not. You cannot couple the photon into a propagating plasma. Okay? So something else has to happen, and that something else is grating coupling. For example, you can use a grating so that the grating wave vector is 2 pi over p, where p is the pitch of the grating. And now you can make KSPP equal to G, and therefore you can excite and you can couple the surface plasma. There is indeed 2 methods to do that. One is the prism coupling. As I mentioned, Ricci and Kretschmann came up with this configuration. The idea is that you have KSPP greater than K naught. So the momentum of the plasma is bigger than the momentum of light. So how do we increase momentum of light? Well, think about it. If you use a medium other than vacuum, other than air, you can bump up K naught by a factor ND, the refractive index of the material. Generally, for most material, ND is greater than 1. If you take glass, ND is, the refractive index of glass is 1.5, something like that. So if you think about this, now you have 1.5 times K naught, okay? So now KD is bigger. Good. But it's not enough, because what you need is that the parallel component of KD is equal to KSPP. So you need now to tune the angle. You need to change the angle so that you find the exact matching condition. And that exact matching condition is found when KSPP is equal to KD sine theta. So you can find the exact angle. If you have a specific frequency, you can choose the angle. You know the refractive index of the glass, and you can excite the surface plasma. Now, this is not in scale. Usually, surface plasma propagate only a few microns, up to millimeters and even centimeters in the long infrared range. Okay? Now, grating coupling, we talked about that before, and again, you can match the momentum by using the grating vector. Now, I want to show you today that we can actually use localized sources of surface plasma polarity. And for example, you can make a tiny corrugation on metal film, like a nano groove. You can make a nano slit. You can make a nano hole. Nano means anything between 50 nanometers and 200 nanometers, or even bigger than that. And you can generate surface plasma by light diffraction. Let me show you how we can do that. So this is a cross-section of the typical device that we can make. This is a metal film, silver, and you have a groove on the left side, and you have a through slit on the right side. This is an SEM image of the groove slit. The slit is a through slit. So if you shine light onto a metal film, do you see light transmission on the back? Have you ever tried? So usually mirrors are called so because they have good reflection. So all the incident light gets reflected back, 95% or more. So therefore, if you have a thick enough film, and we're talking about 300 nanometer thick, it's sufficiently thick to have an opaque property. There is no light transmitted, but where the slit is located. So if you shine light everywhere on this metal film, and you have your slit, light can be transmitted by the slit as well. Now, what happens is that the groove, as you can see here, is excited when you illuminate it with plane waves. So the electric field of the light, of the incident light, is oscillating in this direction, parallel to the plane of the metal. And what happens is you can generate positive, negative charges. It's kind of a colloquial way of saying it. But basically, you have an oscillation of the free electrons. And this oscillation of free electrons can lead to propagation of surface plasma. Now, the surface plasma have a very nice peculiarity. They are evanescent waves in the sense that they are very localized at the metal-electric interface. As you can see here, the maximum of the field happens at the metal-electric interface, and then the field decays exponentially. So there is no field away from it. You cannot see it if you're in a far field. Only if you are in a near field, you can detect it. And you can see here that there is a diffraction lobe. So when this groove is excited with incident light, part of it gets scattered back into free space. Part of it gets excited into a surface plasma polaridon. And you can see these lobes of energy here. And these are actually the surface plasma polaridon. They are carrying part of the energy of the incident wave away from the wave itself and on the side, okay, along the side. Now, what happens? Well, it's a two-step process. So first of all, the groove has to excite the surface plasmon. So the incident light is scattered into a surface plasma polaridon. There is another one that goes the other way around. We don't care about that. So one goes toward the slit. And now you have your reference beam. Remember, to build an interferometer, how many arms do you need? 2 arms. Okay, so you need one. It's the left arm and the right arm, say. But in this case, you have one arm which is constituted by the surface plasma polaridon. The other one is the reference beam, which is the field itself at the slit location. Now you have the total field at the output of the slit. This is a tiny aperture that can transmit light. And the field at the output is the sum of the two. Remember the ripples? You're summing the 2 ripples. So you're summing the 2 waves. One is the incident wave, and the other one is the surface plasmon. And the surface plasmon has a phase difference with respect to the incident wave. Well, there is a reason for it. First of all, if you assume you have normal incidence, the 2 beams will arrive at the groove and at the slit at the same time. So they are still in phase. But now the groove has to excite a surface plasmon, and the surface plasmon has to propagate a certain distance at the speed of light in the medium. That's the speed of the surface plasmon, which means that there is a phase lag between the incident beam and the surface plasmon. And this phase lag can cause constructive or destructive interference. The phase is given by this long expression. It's very simple to understand it. There is a propagative phase, the refractive index of the material of the surface plasmon. D is the distance between the slit and the groove. That's how much distance the surface plasmon has traveled. And then there is a complex quantity. Do you think, why is that complex quantity there? What is the purpose of a complex quantity in an exponential function? Yes, so there is a phase. So if you look at phase shift here, phi, right? Or phi, if you want. There is a real part and an imaginary part in the phase, okay? So what is the real part doing? Let's take a look at it. So you have e to the I times a real part. That's the actual phase. If you take the model, you square that, you can use Euler's equations, and you get a cosine function. Okay, it's a sinusoidally varying function. What about this extra I? What happens when you plug this value into this? What do you get? I times I is I squared. So you get e to the minus d over 2 alpha. So I saw your hand doing this. You see an exponential decay of the wave. What does it mean? It means that the surface plasmon propagates with a certain phase, like a sinusoidal wave, like the waves in the pond. But then there is also an exponential decrease of the amplitude because of absorption. Okay? The metal has ohmic losses. So we have to consider that. You have to take that into account. And here's the experiment. This was done a long time ago, but basically you can see, actually I did this. You can see each point here is light measured through a slit groove interferometer as a function of distance. So we have many devices, hundreds of devices on the same film, on the same silver film. They're very tiny. You cannot see them but with a microscope. And you can go interrogate every single device. And you can measure how much light is transmitted by that particular device. And you can do that at a specific wavelength, say 514.5 nanometers, which is an argon wavelength. And you can monitor the variation of the intensity normalized with respect to a single slit. So one is just one slit with no groove on it. So you can just get light transmitted through the slit. And one is that reference. And compared to one, which is an isolated slit, you get more light or less light depending on the distance between the groove and the slit. So you can see that this goes on for all until like 10 microns, but actually can keep going up to 25 microns at this wavelength. What does it mean? Well, it means that you are actually interfering the surface plasmon wave with the incident wave, and you can see constructive interference at some location, destructive interference at other location. Now, what is the distance between the 2 peaks, say? That's the period of the oscillation. The period of the oscillation is determined by the wavelength of the wave that is causing the oscillation. So the wavelength of the surface plasma, which is given by the refractive index times lambda naught, where lambda naught is the free space wavelength. In this case, 514.5. There is another thing that we can measure from this. Somebody told me before that you can get up to a factor 4 in intensity if you have two beams with the same amplitude. They interfere together and they build up the amplitude, so you get twice the amplitude. The intensity is the square of that, so you get a factor 4. So why is it that we don't get a factor 4 here? There is damping, but you do not see damping here. Damping is usually seen, I'll show you damping here. You see, this is damping, okay? It's a different wavelength. Let's go back just quickly. So there is not much damping of the wave, but there is a damping mechanism, which is the generation itself. Let's go back, take a look at this process, okay? Every time light is incident upon the groove, what happens to the incident light? It gets scattered back in free space. So a little bit of the energy goes back into free space with a certain distribution of angles. And there is a part of it that goes into surface plasma. Not all of the incident beam, E0, goes into ESPP. So the amplitude of an SPP, as it starts from the groove, is not E0, but it's smaller than that. But how much? It depends on the scattering efficiency. There is a factor that's called beta, okay? And this beta goes into the model and tells you how good a groove is as an exciter or as an excitation source of a surface plasma. Okay? We can do this exact same experiment with the same devices at different wavelengths, and you can see how you can go from 400 nanometers all the way up to 1.4 microns. And you can see if you increase the wavelength, of course, the period of the oscillation becomes bigger proportionally. And the constant of proportionality is the NSPP, is the refractive index of the surface plasma, that can be calculated if you know the dielectric constant of the metal and of the dielectric, which in this case is air. And as you can see, if you plot the data, they lay perfectly on the SPP data that you would accomplish by using Radar's equation, by using this equation. So a groove, a single groove, can be a pretty good source. It's about 25% efficient. What does it mean? That 25% of the incident amplitude is transferring to a surface plasma. This is pretty good, because you have to think 25% left and right, and then you have 50% back into free space. That's not too bad. It's localized, because now the groove has a specific phase relationship. It's so small, it's much smaller than the incident wavelength. Think about the wavelength. It's 500 nanometers, but the groove is about 100 nanometers, so it's a fifth of the wavelength. So it's very localized. Now we can do the same thing with a slit, okay? How do we measure the interferometer using a single slit? Well, we can do that by having two slits, one next to the other. We measure light transmission in the far field. Now again, if you have two identical slits and you're looking at the zeroth order transmission very far away, you cannot distinguish the two sources. You have to sum up the amplitudes coherently, right? Which means that you can get up as much as 4 times enhancement in intensity. Let's see if this time it happens. This is what Young did a long time ago, but in his experiment, he didn't include surface plasma. So now we're going to take a look at the different modulation effect that's going to take place, because the surface plasma can now be generated. I'm going to show this again. So light is incident upon the slit, and the surface plasma is generated here. It's also generated there, and at the output mouth as well. So you get surface plasma that are generated on the top and bottom surface, and they can interfere with each other. Think about the waves in the pond. And you can have a modulation of the light intensity from each slit. And as you can see here, this is the experiment. Again, you can make two structures in metal film. The two structures have been made by using focused ion beam milling. So we etch atoms one by one, and we can generate very thin, very tiny slits. So this is about 100 nanometers in width, and this is about 10 micron long. Okay? And you can vary the distance between these two nanoslits from a few hundred nanometers, say 150 nanometers, all the way to a couple of microns. Again, this is a very precise experiment to do. And what you see here is that as you change the distance between the two slits, okay, you get a minimum, you get a maximum, you get a minimum, you get a maximum, and so forth. The maximum is the result of constructive interference between the incident beam and the surface plasma that are propagating on both surfaces. The maximum you can get is what? 4. We're getting 3 point something. And the reason is that this wavelength slit is only 49% efficient. Well, if you think about it, it's pretty efficient because it now means that 49% goes to the left SPP, 49% goes to the right, and the rest is basically not going anywhere, okay? So most of the incident light gets coupled into surface plasmons. There is another interesting effect that is kind of a second-order effect, like a Fabry-Perot cavity. Have you heard about Fabry-Perot cavities? Well, you get two mirrors, and you send light, and depending on the distance between the two mirrors, you can get constructive or destructive interference at the output. And it's basically the same thing. Now, the surface plasmon, they don't just propagate in one direction. They can also be reflected back many times. And actually, this model accounts for the multiple reflections. You can solve it analytically. It's a geometric series, and you can find the red line is the theory, and the solid lines are the experimental data. Finally, I want to show you, and I want to convince you that two holes can also be used to generate surface plasmons. The same experiment, instead of having slits, we have two holes, tiny pinholes. These are 15 nanometer in radius, okay, so about 100 nanometer in diameter. And you can change the distance between the two, and you can do the same thing, and you can see a modulation. You can go up to 2.4, something like that. Now you can see a decrease in this way. The decrease is due to the fact that now the hole is a source, that's kind of a cylindrical source of surface plasma. So there is energy to be conserved. In order to conserve energy, the field has to go down as 1 over the square root of the propagation distance. Okay? So that's the 1 over square root of A here. Again, you can build a model. The model fits pretty well. You get information about the phase of the plasma as well as the efficiency, and the hole can act as an efficient localized source of surface plasma polaritons. So in the end, you don't need gratings. You don't need prisms. They are pretty big and bulky. But you can also use nano corrugations or nano apertures, like slits and holes in a metal film to generate surface plasma. Of course, you need the incident beam to generate the surface plasma. Now, what can we do with this? A little bit of applications. I'll see. First of all, do you have any questions so far? So do we understand how plasmonic interferometry works? Basically, waves that are interfering with each other. One of the two waves is a surface plasma that is only there because the metal is there, and the electrons are there to support it. Any questions? OK. I'm assuming it's all clear, hopefully.
I have a question about the graph.
Yeah.
And how could you measure the amplitude of the electric field in the graphs? You showed some graphs.
Yes. So the graphs I've shown here,
Yes,
for example. OK.
And how it was possible experimentally speaking?
Yeah, so that's a good question. So how do we actually measure the intensity experimentally? So we have a microscope that can take light only from a very small field of view. Indeed, what you do is you use high numerical aperture objective lens. It's about 40x, and you can take a look at the pinhole in the metal. Okay, so what you do, you scan the pinhole. Yeah, you can use a micrometer, or I'll show you later. We have also an automated stage to scan all the structures automatically. It's a tedious work to do. So I used to do that as a postdoc with micrometers, manual micrometers. My students now use the automated stage, so they're much better than me in doing this. But then how do we do this? We need some kind of reference, okay? You can use your eye. You can see if light goes up or down, but it's not quantitative. So we use a photodetector that is calibrated. And we also have a single structure, say one slit. That's close by, okay? Not too close because you don't want to have interference between them. So what you do, you measure light transmitted from an individual slit, and then you see what happens when you have two slits. Okay? This one is the normalized transmittance. Let me go back a little bit because it's an important point here. So I kind of skipped this, but that's where the source of confusion perhaps is. So each slit transmits some light, and you can sum over the different slits, right? So if you have two slits, you get H1 plus H2, and then you have to square that. But in general, if you have two slits by symmetry, H1 is equal to H2, right? The field, it has to be the same. So that you get twice the field at each slit, and you have to square that. You get 4 times, okay? Now, you want to divide that by n squared, which is the number of slits squared, because, again, the maximum enhancement you would expect is 4 for the intensity. But you don't want to see the enhancement due to the fact you have 2, 3, 5 slits. Of course, you're going to have 4 times, 9 times, 16 times more light overall if you integrate over the entire structure. But you want to see what happens at each slit. Okay, you want to see what's the intensity enhancement at each slit because of the surface plasma. And that's why we divide by n squared, the number of slits squared. So this number that I'm showing you here is actually the result of the division by a factor 4. So as a matter of fact, the combination of the two slits transmit 12 times more light than a single slit. But I don't care about that because that's kind of trivial. You just have 2 light sources instead of 1, and that's what you get in the 0th order transmission. But we want to evidence the effects of surface plasma. So we use that normalization. We divide the spectrum, the intensity spectrum, by the intensity at the slit of a single slit. And then we normalize by the number of slits squared. And that's how we end up with this intensity measurement. Okay? So we always have a relative ratio. It's a relative intensity enhancement. It's hard to do absolute measurements, but you can use calibrated photodetectors. Okay, now how can we use this? Actually, there is a lot of things I would like to tell you, and I feel like I would like to gear my talk based on what you care more about. As I told you, we can talk about applications such as plasmonic solar cells. How do we use what we know to excite the efficiency of solar cells, to enhance the absorption in thin films of materials? We can also use this to build beta detectors that can be used, for example, for glucose sensing in saliva rather than in blood. We can also talk about how to measure the optical constants of materials using plasmonic interferometry. Because if you understand interferometry between surface plasma, you can also infer the properties of the materials that support surface plasmons. And we can also measure the coherence length of surface plasmon. I told you before that in order for 2 beams to interfere, you need to have a degree of coherence between them. If you have 2 beams that are not coherent with each other, they cannot interfere. So you just sum the intensity. You get light bulb number 1, light bulb number 2. The intensity here is just the sum of the 2 intensities. But if you have a laser and you split it in half, now the 2 lasers have a phase coherence that allows you to actually get 4 times the intensity if you choose the length of the arms properly. What would you like me to talk about? Any? For you, this one? Okay. So if you take a thick solar cell, typically thick solar cells are made thick because they absorb all of the incident light, right? It would be nice to show, to also have some kind of absorption in a thin cell, but thin cells do not absorb much of the incident light. The reason is, if you take a look at the absorbed energy, there is a lot of loss here. The reason is that the material is too thin to absorb any light. Indeed, close to the band gap of the material, 1100 nanometers, at the absorption band gap, the absorption length for silicon is of the order of 500 microns. So 500 microns, you need 0.5 millimeter of silicon to absorb that light. And the sun actually emits light at 1100 nanometers. But you don't want to use materials that are too thick, because the problem is, how do you make them pure? How do you make them crystalline enough that you can also extract the carriers? So once you generate the electron-hole pair, you need to extract them to generate current. So one of the problems these days is, how do you make a thin film solar cell that has the same absorption properties of a thick cell? If you think about surface plasma, they can give you a hand, okay? They can help out. The reason is that the sunlight can come in a certain direction, and then with a certain efficiency, you can turn this light beam into a propagating surface plasma. Now, let's think about this. You remember about the exponential function and the I in the phase, okay? So there is an exponential decrease of the wave as it propagates. That wave can be absorbed. And the wave can be absorbed in a long distance now, rather than in this direction. So this could be 100 nanometers. But in this direction, the surface plasma can propagate for millimeters, centimeters. The solar cell can be 10 centimeters long, okay? Sooner or later, the surface plasma will be absorbed and will contribute to the generation of electron pairs and will contribute to electricity generation. So what we want to do in my group is to try to come up with a scheme where a single groove or a hole in the metal can be used collectively with other holes to make up for interference so that you can have constructive interference along the direction of propagation of the plasma, and you can have a lot of absorption. So the idea is that, again, especially enhance the band gap. There is many approaches. Most of them are periodic assembly of scatterers or random or aperiodic or random array. So we want to show you how we can use quasi-periodic corrugation like the Penrose style. As you all know, you can map the plane with actually three-dimensional, with triangles. It's fine. Squares, you can map the plane. What about pentagons? Can you map the plane with pentagons? No, there is no translational symmetry. But it turns out that Penrose found a way using rhombi, like the fat and the skinny one. He found a way to map the plane with a structure that shows 5-fold symmetry, actually 10-fold symmetry in the Fourier transform. And actually, this is the structure that I'm showing here. And the idea is that we would like to make a solar cell that has a back metal, which is now corrugated with holes to excite surface plasma. We have a thin layer of absorbing material, which is a polymer, in this case, transparent conductive oxide, and then a metal on top. This is the work that was done by Emily, one of my undergraduate students, and we published a paper in Applied Physics Letter in 2011. So she made a solution of P3ht poly-3-acyl thiophene. It's for chemists. Any chemists here? Perhaps one? No? Okay. So you don't have to learn this name. It's called. There's one? Okay. Hi. So you can pronounce this much better than I can. So this is a P3ht polymer. The idea is that this is a bulk heterojunction. So the polymer can actually conduct electrons. The problem here is that the chain is pretty short. So how do you come up with a way of extracting the electron pair? Well, to do that, you need to have a thin film of the order 20, 24 nanometers, where 20, 24 nanometer is the diffusion length of the exciton in this polymer. So what we made was glass, silver, with corrugation on top, and then the P3ht. And we studied the interference between the different holes, okay? Again, the idea is that you come in on a flat surface, you get reflection back, but if you have a groove or a hole, you can get a sensible fraction of the incident beam coupled into surface plasma that can then interfere. And you can take a look at the mode profile of the surface plasma in air. Okay, it's an evanescent tail here. This is in the bulk P3ht PCBM. This is 24 nanometer of material. This is 150. So typically, this is bulk. So greater than 200 nanometer is considered bulk. Let me go a little bit quick here. So you can map the plane with so many different arrangements of holes. One could be square, like with a high periodicity, high translational symmetry, very low rotational symmetry, though. You can have a random array in which you have no translational symmetry, no rotational symmetry. And there is a huge world in between. It's called the world of aperiodic or quasi-periodic arrays. For example, this one is the Penrose. You can kind of see with your eyes that there is some circles around, right? And these circles are kind of nested with each other. So it's an interesting structure, and I'll show you that it actually works. So how do we make this? Well, we start with a complex plane. It's a little bit technical, but basically there is a mapping algorithm that leads you from complex plane. Okay, you have x and y. Then it maps this plane into points. And you can see this is the point for n equal 3. And you can take the Fourier transform, the discrete Fourier transform of that structure to see the rotational symmetry. Now, if you take a look at the square, of course, you get squares in the Fourier transform. That's pretty simple, nothing new. But if you now take a look at the Penrose style, the tile that had the circles, you see here some of the circles going around. So there is no translational symmetry, but this is still considered a crystal. Indeed, if you take a look at the Fourier transform, you can see a lot of points in the Fourier transform that correspond to crystal lattices of the material. You can also do the same thing with heptadecagrid grid. Oh, can you tell me the difference between random and, well, I told you already. But if you take a look with your eyes, okay, the brain actually is pretty powerful at doing a Fourier transform. Almost all of the people in the audience I interview, they tell me that actually they can tell the difference between random and quasi-periodic. Now, this is an heptadecagrid grid. It's called 17. It has a 34-fold symmetry in the Fourier plane. And if you look closely, do you believe that this is non-random? You see that there is some circles here, for example? Okay, so if you look very closely, it seems like there is circles going around, okay? So indeed, if you take a look at the Fourier transform, now we do it for good, you can see the ring, this diffraction ring, which is actually determined by the rotational symmetry of the structure. So why do we need rotational symmetry? It's an important point. Remember, it's all about interference. If you have 2 points that are at the right distance, so that you have constructive interference, you want to reproduce the distance as many times as you want, okay, as you can. And so what this heptadecagrid grid is doing is exactly that. The fact that you have a ring, almost continuous ring in the Fourier transform, tells you that there is a special frequency that is repeated in real space. And that frequency is the nearest neighbor distance between holes. Now we have one hole with many holes at the right distance to have constructive interference. Then you repeat it, you take another random hole, and there's going to be so many holes around it with the right distance, okay? So that we can take advantage of constructive interference. By the way, this is an optical Fourier transform, just to show you that it's real. This is a real space of the Penrose, and this is actually the tenfold symmetry of the crystal lattice. Now we can get enhancement. I'll skip a few things here so I can go faster and talk about other stuff as well, if you like. But if you take a look at the periodic arrangement, and you calculate the fields at the metal-electric interface, right where the polymer is located, you see that if you increase the wavelength, well, you have, basically you're losing something. The field is roughly staying around 2, 1.5, 2, something like that, okay? But if you look at now the quasi-periodic heptadeca, the array with 34-fold symmetry, rotational symmetry, you get much more intensity enhancement at the surface. Why is that? As I told you before, we are basically favoring the nearest neighbor distance as the favorite in the array, and we're repeating that many times in an orderly fashion. Another important feature is that you can also get, given the same area, you can get many more scatter using quasi-periodic arrangement than periodic arrangement, okay? And indeed, we can enhance the absorption. Okay, this is the optical power absorbed in the quasi-periodic array, and this is the uncorrugated. This is the flat reference surface. Of course, you can also tune this absorption by changing the distance in the whole array, and in the end, you can optimize it. We found out that the best nearest neighbor distance is 300 nanometers. So we're talking about holes that are 50 nanometer in radius, and they're separated by 300 nanometers in distance. And compared to a random array, you get the maximum enhancement possible. You get up to 55% enhancement in this film. We can also make the structure. Of course, the way we make them is focused ion beam milling. I told you that this machine shoots ions that are heavy, like gallium ions, onto the sample, and the material gets removed one atom at a time, or a few atoms at a time. So that's how we can make such small and narrow holes. But of course, this is not practical if you want to, say, have something that covers the entire roof of the Scuola Superiore. So how do you do that? Well, we need to find a different way. One of the possible ways is to do nano-imprint lithography. So you make a stamp, which is typically expensive. The stamps contains your quasi-periodic array. You imprint the polymer, you deposit the material, and you get holes in the metal surface, on the metal surface. So that's what we did, and actually you can see that there is indeed an increase in the short circuit current and the open circuit voltage of this polymer solar cell, which is by no means close to being a world record cell, but it shows the concept that we can actually enhance the photogeneration current in this cell. This is my plasmonic concentrator for solar cell part, and do you have any questions about this?
efficiency of these type of solar shells?
So the P3ht PCBM, those are bulk heterojunctions, which means that there is two phases. Typically, for a thickness of 150 nanometer, you get total absorption of the incident light. Those cells are characterized by
quasi-periodic array, naturally, like self-assembly. Thus.
So, okay, the question is if there is a system that can make quasi-periodic arrays like self-assembly. Well, there is some, like, you know, these sunflowers, you know, they have some periodicity, quasi-periodicity. But in reality, if you wanted to make this artificially in a simple way, you could use many laser beams that are aligned according to the 17 grids, okay? And you can have interference, so photolithography, then you can achieve that. There is some crystal, Sketchman was the first to observe that in crystals that were made of MgO. I don't remember exactly. I don't remember the actual structure. Yes, I think it was manganese, right? Yeah. An alloy with manganese. So it has been shown in 3D, in three-dimensional crystal, and it got the Nobel Prize for that, for demonstrating that you can have a tenfold symmetry structure in real crystals. Okay, so, yeah, sure.
You can use Plasmon to reduce the evanescent contribution in order to maximize the absorption.
Okay, so you want the question is if we can use surface plasmon to reduce the evanescent contribution and maximize the absorption. Now, the evanescent contribution you're referring to is in the vertical direction? Okay, so that the tail. Okay. Yeah, so the surface plasmon is confined at the metal director interface and it decays exponentially away from the surface. Typically, the skin depth, that's called, the name of this typical decay length, is of the order of the wavelength. So if you're using photons of 1 micron, you're going to have about 1 micron of decay length. Okay, so there is only a tiny part of the field interacting with the absorption, with the absorber. So how do we do that? Well, we can do that by using 2 metals instead of 1. And if you take 2 metal films that are also corrugated, the plasmon is confined in that direction because of the interference, but it's also confined in the vertical direction. So the mode extends into the metal by about 25, 30 nanometer, which is the skin depth in the metal. That's the penetration. How much, if you shine a laser into a metal, it's going to penetrate about 25 nanometer below the surface of the metal, and then it's reflected back, okay? But if you take 2 slabs of metal with a specific distance, you can have an antisymmetric and a symmetric mode, which is much more confined than just a single plasmon that is evanescently decaying up to 1 micron. So you can confine it artificially by making a cavity in the vertical direction. Yeah. Okay. More questions? Yeah.
Is like polarization conserved in Topical, for instance?
Okay, so polarization is very important for surface plasma polarity. In particular, you can think about the different structures I showed you. If you take a hole, do you think a hole is going to show a polarization dependence or not? It's, again, a physical question. The hole is rotational symmetric, right? So if you come in with a certain polarization, it doesn't matter which way you're exciting the plasmon. You're going to excite a plasmon that goes in a different direction, but with the same efficiency, right? So that's a rotational symmetric system. The efficiency is constant, it's invariant by rotation. Now, if you take a slit, the narrow slit is a different story. Actually, narrow slits are good polarizer. You can think about that because you're going to have a mode that is propagated, that's called the TE mode. It's generally propagating because it's guided, it's not cut off. If you have an electric field that is parallel to the long axis of the slit, basically the electrons is setting into motion the electrons in the walls, okay? So you have these big walls, and you have the electric field driving the electrons of the walls. There is a lot of damping. So the field is attenuated, and there is a cutoff condition for that mode. So the slit is acting as a polarizer. And indeed, if you want to excite a surface plasma using a slit or a groove, the electric field has to be perpendicular to the long axis of the slit. That's one of the reasons why if you have a grating, the grating is good and is efficient at a specific polarization. Usually one of the two, the S or P polarization is more efficient in terms of the grating of the diffraction effect. Gratings to me are not good if you want to make a plasmonic solar cell because, again, sunlight is randomly polarized, okay? So if you're coming in with light that is randomly polarized, plus there is scattered light because the sky is blue because of that, all of that light has no specific polarization. And you can say that during the day is averaged, okay? So then gratings are not a good idea. On the other hand, if you take holes, they are a good idea because no matter how the hole is excited, the hole can generate a surface plasmon. And if you use highly rotationally symmetric structure like the quasi-periodic structures, it doesn't matter whether you change the polarization. Indeed, the enhancements I showed you, the 55% enhancement in absorption, is with randomly polarized light. You can get even higher enhancement if you use a specific polarization, but this is an average value. You mentioned Fabry-Perot. So the Fabry-Perot, so the surface plasmon is a transverse magnetic mode. If you take a light beam propagating in free space, okay, there is 3 numbers to characterize the wave. One is the propagation direction, K, the K vector. The other one is the electric field, and then you need H. Well, usually you need 2 because there is a relationship between E, H, and K, okay? E cross H is K, okay. If you take a surface plasmon, the surface plasmon has a mode that propagates in the direction of the oscillation of the field. Okay, so the propagation direction of the surface plasmon is also the propagation of oscillation. So this is a longitudinal mode which cannot exist for electromagnetic waves. It exists for other kind of waves, like phonons. That is known. Plasmons are a hybrid wave because they are in between transverse and longitudinal wave. Indeed, they have both character of electromagnetic wave and oscillations of phonons. They're called plasmons. Polarization is fundamental because, again, surface plasmon will keep memory of the original polarization state of the incident beam. Okay? Indeed, the plasma that will propagate away from the slit will do so recalling the direction of propagation of oscillation of the electric field. Other questions regarding this part? Yep.
How about localized surface plasmon in the solar cells? Are they more promising than surface plasmon light?
Well, as you know, there's many groups working in the field and people using plasmon particles and people using gratings. My understanding of the problem is that single particle can work as well. The only problem there is that they are usually arranged according to random arrangements, okay? And random is never the best option, not even periodic, as we found in this case. If you want to benefit from surface plasma, you really need to use quasi-periodic arrangements of such structures. So you may as well use localized plasmons. But then again, you want to be away from the resonance condition because then you also have a lot of absorption in the metal. There is no way you can use that to generate electron pairs. So you have to have a little bit bigger particles. You end up having 200 nanometer, 300 nanometer big particles in the film. Some of the papers report structures on the top surface. To me, that's not a good idea because it's like you're shading your device. So if you think about a solar cell, you want to have most of the incident light go through the absorber and generate electron pairs. But if you have a partial mirror on the top part, that's not good. Of course, other options are to place the scatters in the middle or at the back contact. But then again, it's all a question of engineering light-matter interaction. And if you understand how light interact with one piece of the puzzle, that's only one part of it, because then the collective oscillation or the collective interaction of the different particles or holes is also important. And so if you could do that, if you could use small particle, but arranged according to quasi-Superiore arrays, I think that would be a winning design. Yeah.
I said before that gratings is good only for certain polarization, but could it be more efficient a polarizer on top of the solar cell and gratings? Could it be more efficient than holes in a quasi-periodic range?
So if you use a polarizer, well, again, if you have randomly polarized light and you're using a polarizer, you're already losing half of it, right? So the answer is no. Unless you have a complicated scheme in which you separate light beam like they're doing for multi-junction solar cells, you can take a little slice of the solar spectrum and send it to a specific cell that's been optimized for the particular range of wavelengths. Perhaps you could do the same thing by using different polarizations. So you can split the incident beam into two different polarized, two different directions perpendicular to each other, and then you can use two structures that are optimized for those two particular polarizations. But then again, you will have to spatially localize the two cells. More questions? You want me to continue? Okay. So again, I think we have to stop in about 15 minutes. But this part I think is very intriguing. I'm one of the most part that I'm most interested in doing. And actually, it consists in basically expanding the idea of plasmonic interferometry. Instead of using one arm and the incident beam, we're going to have now multiple arms, two grooves and one slit at the center. The same thing is going to happen. You're going to have each groove be a source of surface plasmon polaritons that propagate toward the slit, and they can interfere. At this point, you have three parameters you can play with. You have wavelength, you have P1 and P2, the two arm lengths, and you also have the refractive index you can play with, or you can measure in this particular system. So the way we do it is we start with a quartz slide. We deposit silver. We make the plasmonic interferometers using focused ion beam. There is an automated script that can mill up to thousands of interferometers with precision. And this is one such interferometer. You have 10 micron long slit grooves, and the distance P1 and P2 can be varied accordingly. And you can also make a microfluidic channel, so you can use it to flow whatever analyte. It could be blood, it could be saliva, it could be anything you wish. And then you can measure the properties of the plasmonic interferometer under the different flow conditions. This is a typical setup. So this is a condenser in the microscope. This is the tubing in the microfluidic channel. The chip is below it. And actually, you can see that there is many arrays, many interferometers. So we measure each individual array one by one by looking via a monochromator and a CCD camera. So we acquire the spectrum for each device. Now, this is a tedious work, but it's automated. So we can do it for 1,000 devices. You just do a triangulation, and actually you can measure all of the devices in the matrix. So how does it work? Well, we start with a single slit. The single slit has a certain intensity. Intensity is the square of the amplitude being transmitted. Very broad. This is typically determined by the lamp in the monochromator. And actually, we normalize it by itself. What we get 1. Very simple, trivial. But now, what if you have a slit and a groove next to it? Okay, again, we measure the blue spectrum is basically the groove slit pair, and the dashed line is the single slit, and then you divide one by the other, and you get this normalized groove slit transmission spectrum. Some wavelengths are enhanced, some wavelengths are suppressed. Exactly the same thing. We're changing the phase of the plasmons, we're fixing the arm length, and we're getting this kind of interference. If you have two grooves and one single slit, you get more modulation, you get more peaks, you normalize by the single slit, and you get this typical spectrum, okay? Now, how do we use this? We use this to monitor changes in the refractive index, for example. Now, let's take a groove-slit groove plasmonic interferometer with a distance of 0.57 microns and 1.85 microns. The precision here is pretty high. We make it less than 1% error in this kind of measurements. Now, if you, instead of having air, you flow water, what happens is that you see a change in the spectrum. In particular, lambda 1, lambda 2, lambda 3 move, lambda 3 disappears from this range, and another peak comes in. Most importantly, you can see that there is a minimum turning into a maximum. So the very same device is showing two different behaviors, whether you have air or water. In one case, it transmits more light. In the other case, it transmits less light. So this is a sensor for refractive index. And the sensitivity of this device is delta lambda, wavelength shift, divided by delta n, the change in refractive index. And if you go from air to water, you have only 0.33 change in refractive index. So you can calculate delta lambda, you get the figure of merit, which is pretty high, actually. Another thing you can do, you can change, so you place water, but in this case, you change the arm length. You make it longer. Well, if you make it longer, you can allow for more surface plasmon modes to interfere. And indeed, you get a condition where you have kind of the same envelope function, but many more peaks. And the full width at our maximum goes down. It's about 13 nanometers. Sensitivity is improved. Why? Because now you can track the peak better, in a better way. Okay? So you're going to see a shift in the peak. And since it's narrow, ideally, you would like to see a delta in this system. Now you can build maps. Now, this is a simulation map, but I'll show you experimental maps shortly. The idea is that you take a spectrum, a normalized spectrum, like the one I showed you before, like this. Okay, you take this spectrum, and you stack them vertically. So now it's a color map. You see, bright means high intensity. Blue is lower intensity, lower than 1. 1 is no enhancement. Again, red is 1.5. So this is enhancement, suppression, enhancement, suppression, enhancement. It's basically the same spectrum, but now in color code. And you can do that for all the devices that you have. You build this color map, which is a signature of the plasmonic interferometer. Indeed, I'll show you here that we can build, these are experimental maps of the plasmonic interferometer. We are fixing the left arm to 400 nanometer, varying the right arm from 0 to 2 microns. And we are now changing the left arm. You see many more peaks coming in. And you can model this pretty precisely. Why is this important? The map is more powerful than a single spectrum. The map can tell you at once visually what you have on top of your device. We did that with air. So let's say you have silver air. You have many interferometers. You build the color maps, high intensity, low intensity, and so forth. And now take a look what happens when you have the water instead of air. You see a drastic change in the entire color map. You see this is the red region now becomes clustered all the way here. You see many more peaks and valleys here. And again, you can model it pretty well. Now, the color maps can give you the fingerprint of the material you have on top. Because you can do spectroscopy, you can find out the refractive index of the material. Then we decided to choose glucose as one of the analytes of interest. The reason is that there is 350 million people that are affected by diabetes. And basically, this is caused by an excess, well, one of the symptoms is an excessive glucose level in the blood. And the typical glucose levels are the order of hundreds of milligrams per deciliter. So you need blood to measure the glucose level using your fingerprint. And you can also use the electrodes that you can buy commercially. They're commercially available. So we wanted to choose this because, again, it's relevant clinically, but it's also a difficult problem because glucose is small. It's a small molecule. It causes very small change in refractive index. So how do we measure it? Well, again, we built this plasmonic interferometer. This is the glucose molecule. It's not in scale. Glucose molecule is 1 nanometer, while we're talking about hundreds of nanometers for the width. But just to give you an idea, that we want to take a look at we want to sense the presence of glucose by using plasmonic interferometry and photons. And here's the experiment. Remember one of those curves for normalized transmission? You see maxima and minima. One is the single slit. Now, if you change glucose concentration, you go all the way up, you see a shift in the peak position. And you also see a change in the intensity. So the intensity, relative intensity, is changing as well. You can choose 2 different wavelengths. You can take a look at the sensitivity curve, delta I over I naught. You're basically calibrating your sensor. Now you have a sensor that can tell you, given the value of intensity, it can tell you how much glucose you have in solution. And this is the typical thing you can do with very small interferometer. Actually, I'm going to zoom in right away. if you zoom in one of those panels, you see that this is the typical range in serum blood, and this is the range in saliva. It's about 100 times smaller, and we are able to pick up that change, which is promising because typically glucose meter can only detect very high concentration that are typically present in blood. So now we have a sensor that potentially can allow us to measure glucose in saliva. Let's see how we do that. Let me go a little bit quicker here. So one of the problems is that glucose in saliva is not just the only element you can imagine, right? You're going to have a lot of proteins. You're going to have a lot of cells. You're going to have enzymes like the amylase. Have you ever eaten popcorns while watching a movie at the cinema? It's kind of sweet, right? Yeah? No? The popcorn, you keep it in your mouth, and it's a little bit of sweet, like sugary. The reason for that is that there is an enzyme, it's called amylase, that transforms the amide in the popcorn into glucose. So basically, the first digestion is occurring there. Anyways, there is a lot of things in saliva. So how can we tell glucose apart from all the other things? That's where we came up with an idea to use a dye chemistry that consists in the following. You have a reaction that takes glucose, which is optically transparent, inactive, and transforms another molecule into an optically active molecule, which is amplex red. This is the reaction. We start with glucose. We take an enzyme, which is glucose oxidase. The enzyme reacts with oxygen and with glucose, and it transforms glucose into something else that we don't care about. We disregard that. The byproduct is H2O2, which is aqua oxygenata. Okay? So this aqua oxygenata can interact with horseradish peroxidase, which is another enzyme, and transform an amplex red molecule, which is colorless, into a resomorphic molecule, which is red. What happens is that you take your cocktail, you spit in it, and the glucose in your saliva will transform the solution and will make it red. And once you do that, you can pick up the color by using your interferometer, which is very compact. You can use very small volumes, picoliters, instead of hundreds of microliters. And that's pretty sensitive as well. So that's the typical example. So we put everything in the reaction cocktail. It's the glucose oxidase, the horseradish peroxidase, the amplex red. If there is no glucose, the reaction doesn't happen. If there is glucose, the reaction does happen. Let me go a little bit faster. You can see here how the plasmonic interferometer can indeed see the change in intensity because of an increased absorption. So the solution becomes red. With your eyes, you cannot see that because it's very tiny. It's kind of pink, but you cannot see it with your eyes. You can quantify it with the plasmonic interferometer, which is so sensitive. And let me go a little bit faster. So can we measure it in saliva? Well, first of all, yes, we can. We've shown that we can. We can also show that we can measure it in artificial saliva. Saliva is made of components that are well known. They are indicated here, salts, different kinds. There is urea, which is one of the biggest components. So if we take away all the proteins and the enzymes that can be filtered out, the only components that are here. You can make an artificial saliva. That's the recipe. There is no biologist here. Usually the biologists say, oh, we could give you saliva. You don't need to make your own artificial saliva. So, I know. Anyways, yeah, that's what they say. They laugh at this graph because they say, oh, you don't need to make artificial saliva. But we do. And indeed, this artificial saliva is made just to make sure we can reproduce the results, which is one of the important things in science. As you can see, artificial saliva is this red curve that shows that we can measure concentration. Now, the three reactions have a time constant associated to it. I'll go very fast, but the assay that you can come up with has a time constant of 30 minutes. Can you think yourself waiting 30 minutes to measure your glucose levels? No. So we wanted to speed it up. So we had to study the reaction kinetics. So that's what we did. We wrote down a set of rate equations that tell you a little bit complicated, but nothing really too complicated. So the glucose is being chewed up by oxygen. This is a minus sign in dGdt. And you're making H2O2, aqua oxygenata, with a certain rate, K1G. It depends on how much glucose you have, and then so forth. Okay, so you can solve the different components And you can take a look at the typical times, and you can see that the time scale can be shortened if you increase the concentration of horseradish, actually of glucose oxidase. Okay, so if you have more glucose oxidase, which is the enzyme that drives the reaction, you can actually make this into a time that is about 200 seconds. So it's about 2 minutes. So you can live with that. Okay, especially because the time it takes to do a measurement is about 1 minute. So we're trying to build something that works in a range of micromolar instead of milligrams or hundreds of micromolars. So it's between 20 and 240 micromolars instead of millimolars. The glucose specificity has been demonstrated in artificial saliva. The assay time has gone down from 30 down to about hundreds of seconds, okay, which is pretty good for this assay. Then the long-term goal would be to try to actually make a chip that contains different linkers or different chemistries that can recognize specific analytes. It could be glucose. For example, it could be insulin. It could be cytokines that are generated when you suffer a hit. Okay, so if you're hit by somebody, your body responds with a reaction by generating these signaling proteins that are called cytokines. They're very small. So think about a chip that has millions of interferometers, and each interferometer is specific for a specific analyte. Glucose, insulin, you can do an entire panel using your saliva or your blood. Okay, that's kind of the long-term goal of this research activity. Do you have any questions? I can be done here if you want. I mean, I have more stuff. We can talk all night long. Any questions regarding the sensor, the biosensor? It's all clear? Okay, so the enzymatic reaction, the kinetic constants actually do depend on temperature and also on most importantly, on the pH of the solution. So the pH is very strong in determining the constants. One thing we'll have to do, if you think about an application of this, a real-life application, the device will have to calibrate itself with respect to the environmental parameters. For example, the saliva could have a slightly different pH or slightly different components, so you'll have to run kind of a reference sample for that. And then the assay, of course, the timing will depend on the particular pH. Well, we hope that we're going to have times that are going to be much more than typical measurement time, so that won't affect the reading of the signal. Okay, more questions? No? Okay. So if not, let me skip quickly to the end. We can measure, well, I don't have time to measure coherence length, but that's the summary. It shows you that basically, hopefully I've shown you that we can use plasmonic interferometry, first of all, to understand something about surface plasmon, to understand the phase of propagation, the amplitude of the scattering event. We can control the interference in plasmonic solar cells, and we can use it to our advantage to make very high efficiency solar cell in principle by increasing the absorption enhancement in thin films. We can also build high throughput biosensor that can be integrated in a compact fashion because the interferometer is 10 micron squared in area, so you can have millions of them in 1 centimeter square. So we can scale this pretty much similarly to what we had done with microelectronics, where the small size of the device allowed us to have a lot of computational power. In this case, we can also have a lot of computational power in terms of sensing. So we can sense many species at once. Okay, thank you so much for your attention. Sì, ciao, ecco.
Sono tornato giusto adesso.
Sì, abbiamo finito ora, abbiamo integrato la question and answer con il talk, quindi abbiamo finito in tempo. Ok?
Ottimo, com'è andata?
Bene, sì, penso
grazie,
bene.
grazie ancora.
No, grazie a te per l'invito. Grazie mille.
Hai fatto tu il seminario, quindi...
Un saluto generale, Emanuele. Ciao. Ciao Emanuele.
Ciao a tutti. Ciao, ciao, ciao.
Ci vediamo a San Francisco allora, ok?
Sì, con piacere.
Grazie ancora. Ciao.
Ciao, buona serata. Ciao.
Ciao.
Ciao, un attimo, sono in aula, mi sentono in aula? Mi sentono in aula? Andrea?